we present neural architecture search for deep image prior. Deep image prior was introduced by Hailin et al. In CVPR 2018. The core principle of deep image prior is to learn a generative CNN to reconstruct an image X from a noise field. So in this example, the MSE loss is formed between the output image, which is created by this learned function G from the noise field, and the input image X. Now in classical deep image prior, Hailin et al. Propose a symmetric encoder-decoder network architecture with skip connections, comprising 5 pairs of convolutional and up-convolutional layers within the architecture. And this architecture varies across several tasks that are presented in that paper. So denoising, JPEG artifact removal, inpainting, super resolution. But unfortunately, to get a high quality output from deep image prior on these tasks, it's necessary also to hand tune that encoder-decoder network architecture, not just for each task, but also it's content sensitive. You need to do it for each image that's being processed. And therefore, we present an automated method to find an optimal architecture for deep image prior given an image and task. So here we're showing the architecture space searched by our technique. We can see that up to n encoder and decoder units may be present in the encoder-decoder network structure. And we refer to these units as E, N, and Dn respectively. And these bypass connections are encoded as binary flags that enable units to be skipped. So in reality, we can get fewer encoder or decoder stages in our network that's being proposed. So in our NAS approach, we search for the optimal architecture, as I say, using a genetic algorithm or GA. And the binarized representation of the architecture runs to about 100 bits, and it can be considered, if you like, the genome or DNA of the solution. So a GA simulates the natural selection process by modeling a population of individuals, which here are points in this binary space, in this search space, and breeding those individuals together over successive generations to create better and better solutions. So for this, we need a measure of fitness for each individual, for which we use the perceptual LPIP score, and individuals are selected stochastically with a bias to this score and bred together by splicing their genome at a random crossover point, and bits in that genome are randomly mutated or flipped with a low probability to introduce diversity into the population. So here we can see a large image on the top left to be inpainted using deep image prior. The mask is in red, and below it's our best solution, so the output of the best network found. It's also highlighted in the red square here. These rows show the best, middle, and worst individuals, well, sampled from a population of around 500 at generation 20 in the middle and at generation 1 on the right-hand side. And you can see that the visual quality improves in later generations. And here we compare against the network architecture proposed in the code accompanying the IJCV journal version of that deep image prior paper. So that's the dashed blue line. And we can see in the case of inpainting and denoising, our asymmetric networks perform best, although interestingly, we don't hit best performance by optimizing that T, that epoch count. But for super resolution, a symmetric encoder-decoder representation performs best. And we're quantifying here using PSNR and also structural similarity, SSIM. So this t-SNE visualization in the architecture space shows the best performing architecture for images of 8 different artistic styles from BAM, which is the Behance artistic media dataset of artwork. And interestingly, the architectures are clustering according to style without any supervision. And this is the image inpainting task here on the right. And this offers 2 interesting opportunities. Well, first of all, the use of this DIP architecture search as a way of performing unsupervised clustering and discovery of image style. But second, in practical terms, a way to use our NAS technique for image editing and interactive applications. I mean, one could classify the style using an auxiliary technique, like a style classifier, and then initialize the architecture search local to the relevant cluster of known good architecture. So here are just a few more examples of visual results for the 3 tasks: inpainting, denoising, and super resolution, and there are many more in the paper. And we show on the left an example of a discovered encoder-decoder architecture versus, and that's in purple, versus the original proposed architecture in the deep image prior paper in orange. And the graphs on the right are investigating the best performing mutation rates for our representation, which are around 5 to 10%. So in conclusion, we've proposed the first neural architecture search to optimize the encoder-decoder backbone for deep image prior, and our work was developed over the summer of 2019 and published on arXiv later that year. We've proposed a GA to search the network architecture in 100D binary search space and shown quantitative improvement via PSNR and SSIM over classical deep image prior architectures. And Although we didn't have time in this talk to show it, we have a perceptual user study on Amazon Mechanical Turk that shows user visual preference agrees with these PSNR metrics.